classical counterpart. We say every gate, right, maybe not the phase shift gate, but most of the gate we have seen now have a classical counterpart. And how do we define the gate? We define how it transforms, how it rotates the basis vector, right? So what does a Hadamard gate do? Again, we define in this way. For 1 qubit Hadamard gate, we say H operates on 0, becomes 1 over square root 2, 0 plus 1. Is that okay? Do you have classical counterpart? No, right? You have a register which is 0, and you do an operation, it becomes 0 plus 1. In the classical computer, we say your computer has error, right? You don't know only 50% is 0, 50% is 1. And we know this is what? Plus state. Or you can say it transforms 0 to plus. How about when you apply the Hadamard gate to 1? By definition, right, in principle, you should not know how to answer this question if you have not learned it. It transforms to 0 minus 1. So, which is negative, right? So this is the definition, like what we have been doing for other gates. In order to do this, of course, I will just put a matrix, and I claim that this is the matrix, right? All you need to do is just check it. Let's check if this is correct. For example, Hadamard gate applied to 0 means it is 1 over square root 1, 1, 1, negative 1 applied to 0. What is 0 again? 1, 0. When you measure 0, what happened? Not related to it. When you measure 0 states, what happened? You get 0. Okay, remember, okay? Just like the same basis. Exactly. I mean, measure in the 0 and 1 basis. Good point. Okay, what is this? 1 times 1 plus 1 times 0. 1 times 1 plus negative 1 times 0, right? This is 1, 1, right? Which is equal to plus. Is that okay? Right? So you can track yourself again similarly. H applied to 1 equals to square root 1 negative 1, right? You can check it. I won't show you here. But here, I hope you can memorize. Memorize the definition. Why do you need cheat sheet? Memorize it. It's easy for you compared to other classes. You know, E124, you need to memorize the output impedance of common gates with common source with degeneration. That's much more difficult, right? This is easy. 1, 1, 1, negative 1. Memorize it. Okay. Here I do want to say one thing about the inverse of the Hadamard gate, right? So inverse means what? The reverse direction. And it happens that inverse of the Hadamard gate equals to Hadamard gate itself. Okay, so if you have a circuit that starts with Hadamard gate and followed by inverse, it's just the same as 2 Hadamard gate. Okay, so let me prove to you that it is true. First of all, we also take this opportunity to review how to find the inverse of a matrix. The inverse of matrix is 1 over the determinant of the matrix. This absolute value means determinant. It's okay, you forgot what is determinant, you can always Google. And then inside the matrix, you have this so-called cofactor and minor, negative 1 I plus j, and then the m I j transpose, right? Let's write it down first, and then I will define this to you. I make it so complicated because this is the general expression for the inverse. It might be useful when you do 2 qubit or more. We won't use that much, but I want you to be aware of this complexity of the inverse. For 2 by 2 matrix, it is easy, right? So what is that? First of all, let's find the determinant. The determinant is also complicated, right? But for 2 by 2, it is easy. The determinant is what? Let me just remind you, the Hadamard gate is 1 over square root 2, 1, 1, 1, negative 1, okay? So the determinant is 1 over the square root 2. And how do you do it, remember? Very good. Right. It is 1 times negative 1 minus 1 times 1, right? You go in this diagonal minus the diagonal in other direction. And this is equals to negative square root 2, I believe, right? Because this is negative 2. Is that okay? I will slow down a little bit. Is that okay? What do you think? Yeah, minus 2 over root 2 is what? 2 divided by root 2. Negative root 2, right? Okay. Good. Okay, so then what is the meaning of this guy? This is talking about the ith and j elements, right? Ith row, j column. Okay. First look at M00. How do you find it? The way you find it is just draw a line. Maybe let me show you. You do this. 00 is where? This is 00, right? So remove this guy, remove this column. Okay. And then you find out the determinants of the rest. Okay, so this is negative 1. How about M01? Let's look at it again. Which one is our target? 01, this one, right? Remove this row, column with this row, so this is equal to 1. Zeroth row? Yes, you're right. That becomes 1, 1. I'm sorry. I should. Yeah? Thank you. So still 1. Okay. Yeah. Why is the first one? Because you remove this row and this column, you only have negative 1 left. M10, what do you get? 1, 0. This is 1, 0. Right? So you get 1. The 1 is left. Okay? And eventually, M11 equals to, what is M11? That is the mistake I made just now, right? It's 1. Okay? Say again? Oh, yeah. Again, that is typo, not half. That should be square root 2. Yeah, and then I think I missed a lot of stuff. Hold on. Sorry. So I missed a lot of stuff actually. Sorry for that. So should not be 1, right? Should be 1 over square root 2.
That's 1 over h.
Is this okay? Because this is the whole matrix, right? The whole matrix is 1 over square root 2. Right? You can just put 1 over square root 2 inside. Instead of 1. I missed the 1 over square root 2. The whole thing is wrong. Okay? Yeah, if I did not have this 1 over square root 2, I was right. Negative 1, 1, 1, right? But now I have 1 over square root 2. So I need to multiply by 1 over square root 2. I make the mistake. First of all, it's 1 over square root 2, not 1 over 2.
So you're calculating the whole expression.
Before what?
Whole thing.
Yeah, the whole thing. Yeah, the whole thing. No, I'm not only talking about Mij.
Only MJ.
Yeah, Mij. Okay? That's how you find the minor. Okay? Okay, so then what is the result? 1 over, this one is 1 over, I hope I'm right. 1 over, because now it's completely different from my cheat sheet. Negative square root 2. Good, thank you. This is okay? 1 over h. Right? 1 over negative square root 2. You need to be very careful. I also saved the transpose. I don't do it yet. The first one is 0 plus 0. So this negative to the power 0. Right? The second one is negative 1 to the power 1. Negative 1 to the power 1. Negative 1 to the power 2. Right? For this cofactor. Okay? And then what is Mij? Negative 1 over square root 2. 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 Right? Because this is 1 over square root 2 from here. And I also don't need to do the transpose because obviously they are symmetric. So this transpose can be gone when I swap them. So I'm going to take out negative 1 over square root 2. Okay? And I think I really make a mistake here. The Hadamard, let's check, right? The Hadamard determinant is this times negative 1 minus 1. So it's negative 2. So negative square root 2. So I put negative square root 2 here. Yeah, 1 over square root. Yeah, but
I think that I couldn't understand.
yeah, but the matrix you just think about should put the 1 over square root 2 inside. Right? Just factor it out. The whole matrix is 1 over square root 2. Yeah, in my cheat sheet, I did put this as negative 1. But that it looks like, what did I do wrong?
Maybe we impact.
No transpose, you just switch. I still have 1 over square root 2. Supposed to look like this one. Yeah? Yeah, if I take this 1 over square root 2, negative 1 out, right? Then this become 2, right? This negative 1 over square root 2, they all take out, right? And I take negative out, so this is 1. This is also 1, because this is negative, this 1 is negative, right? Then it should be equal to h, but
So I think it's
that's right. But is it, I do something wrong about the determinants or something? 1 times negative and minus 1 times 1, negative 2. Yeah, I did something wrong, very wrong here. The determinants is not this way. It should not be calculated in this way. Because this 1 over square root 2 should go in. Okay? So I did something very wrong. I cannot take out this 1 over square root 2. Okay? I need to put inside. So that's what happened. Right? So I should put this as 1 over square root 2, 1 over square root 2, because this is the matrix. Correct? So this becomes 1 over square root 2 times 1 over square root 2, which is minus, and minus 1 over square root 2 times 1 over square root 2, right? I was missing 1 over square. So this one give me what? Minus 1. Thank you. Right? So this is 1 over minus 1. And this is, if I take out the stuff, it's 1 over square root 2. Right? So this is h, right? Sorry for wasting your time, but maybe you forget this. I don't expect you to do this in the exam. You don't need to know this because it's easy to forget. You can Google when you need it. But I really hope you to learn all this problem. Do not, like what I'm doing here, right? It looks so straightforward to me to factorize 1 over square root out. But it is not. So in the future, when you do this type of program of calculation, be more careful. Don't make the mistake that I'm doing. So my cheat sheet was wrong, but 2 wrongs make 1 right. So my result was correct. I was wrong here and wrong here, but now everything is correct. Yes, actually, I only grade based on answer. I only check the step if the answer is wrong. Okay, this is a hint. Okay, very good. I think we learned something. Just be careful. We learned that we need to be very careful when we play with the matrix. Okay, good, right? So, but I don't require you to do anything, but hope you train this skill because in the future you do linear algebra forever, you need to be careful, right? But the main point, the only thing you need to memorize for this class is the inverse of the Hadamard gauge equals to itself. Okay, very important. Now we want to look at some very terrible math, but very important. When I apply a Hadamard gauge to n qubit, what happened? I already know that when I apply the Hadamard gauge to 1 qubit, it becomes a superposition, right? What if it is n qubit? What does it mean? In n qubits of 0, it means, right, in an n qubits, we have Hadamard gauge, I'm going to write in this way. Tensor product n times. It means nh, not n tensor product, right? It means I have h, tensor product h, tensor product h, tensor product h, and I have nh. Okay, I have nh. Okay, and then of course, some people write it in this way. That's also okay. It means nh, not n tensor product. Okay, you only have n minus 1 tensor product, right? And this is what kind of space is this? I have n, what's the space? To the power n D space, right? Or is the C to the power N space? Okay? So I have a function. I want to know what it is when I apply the Hadamard gauge to the zero stage of this high dimensional space. That is the question here. Can you guess what would it be actually? If we apply to 0, it becomes 0 plus 1. Now I apply to n0, what would it be? A hint is about superposition. Superposition of what? 0 to 0 to 0, 1, 2, 3, 4. All the basis states. Okay? In a one dimension, we apply to 0, it forms a superposition of all basis states. In a 2 to the power n dimension, right? N qubits, it applies to all the basis states. That I'm going to show you, right? So what is this? Again, we know very well this one is nothing but what? I just write it out clearly. The so-called N0 is the tensor product of N0. And that's why for each of the operator, you must only apply to the corresponding space, right? The first electron, the second electron, the third electron, all the way to the nth electron. Right? Is that okay? We talked about Hilbert space before, right? You apply the operator to individual subspace, and then you do tensor product. It's the same as you do the vector tensor product first, and then apply the overall operator to that composed vector, right? That is what I'm doing here. But now know very well what is n, hn, right? What is that? Remember? Anyone remember we just learned?
Remember, every time you take a H will be itself
Yeah, but apply the h to 0. What will it be? Becomes a linear combination, yes. Right? This is the first qubit. And this is the second qubit. And you will do the same thing for all qubits, all the n qubits. Make sense? And then what do you do? Just do a tensor product across them. You obey the distribution law, right? How many 1 over square root 2 do we have? Huh? N only. So it says I can write as 1 over 2 to the power what? N over 2, because it's square root, right? So it's divided by 2. 1 over 2 to the power n over 2. Now let's look at what are the possible combinations. I can have 0 times 0 times 0 all the way times 0, right? I will just write it out. Right? I also can have 0 times 0 times 0, and then the last one I times 1. And similarly, I can have 0, 0, 1, 0. And basically, you see that it's just a permutation of all of them. And the last one will be 1 times 1 times 1 times 1. Before that, it's 1 times 1 times 1 times 0. Okay? This is in binary representation. In decimal, what is this? What is 0? How about the next one? 1. How about the next one? 2. And then? What is the last one? What's the last one? I have N1. What's that? Just make an example. For example, say again. 2 to the power N minus 1. If you feel confused, just substitute N equal to 2. Right? It's 2 to the power 2 minus 1. It's not 2 minus 1. Okay? So I can write this as what? 1 over 2 to the power N divided by 2. Summation x equal to 0 to 2 to the power N minus 1 x. The main point is, it is an even superposition of all basis states. This is very important because in quantum computing, you use a lot of superposition. How do you create them? You use Hadamard gate. Two to the power n minus 1 is the value. For example, 2 to the power 2 minus 1 is 3. Which means you have 2, 1 in binary. Yeah. Here, these are all you learn in classical computer. All these registered value, right? So time's up, we will stop here. Thank you.